For me, the main benefit of being here is that I have a dedicated week to actually just do the conference and nothing else, because if I try to watch it online during work hours, it's very difficult to not get distracted.
So this talk is about work contracts. This is a system that I've designed specifically as a replacement for existing systems that do task-based concurrency. This is designed for low latency environments. A lot of times, the systems that are designed with task-based, they don't scale well enough such that we can make small little tasks and eliminate the overhead sufficiently for low latency. So the systems don't generally work well in that environment. The system was built to replace that. So many times in my life I've found that if you go back to the beginning, the principles, and you question what was done, you can come up with new solutions. And so this quote is pretty accurate here, that in order to improve things, sometimes you have to step back and say, what did we do wrong? How did we get here? Even if things are working. So if we're going to rethink task-based concurrency, what is there to rethink? It's already been done, right? We have all kinds of libraries and tools. Well, how about the task queue? I'm going to show you that I believe that the task queue is a terrible, terrible container for tasks in general. We all know that task queues can suffer from contention. They don't scale well. So as soon as you add a few threads, the performance will begin to degrade. And after a few more threads, you'll actually get worse throughput than if you hadn't added more CPU in the first place, because the contention is too much. We can see that, and probably people know this already, but we'll go through it very quickly. As tasks come into the back of the queue, there's contention. Now that's not a lot of contention for most algorithms, but it's there. You've got multiple threads trying to access the same memory and jockey for position on the atomics. Mostly the contention is on the front, when you've got all of these threads reaching into the front of the queue, trying to be the winner to extract the thread, and the more the task. And the more threads you ask, the worse it gets. One thing I'd like to point out about these containers is that they move the data, the tasks, to the threads. This is common. This is how we think of things. But if we take a system and flip it around so that the threads come to the work, and we make sure that our threads go to different work, then they'll have less contention. Here, all the threads are waiting on the same exact location, and that's why there's contention. So let's see if we can improve this by coming up with a different container besides queues. I think I've touched on most of this. Now with queues, we've got problems with scalability, we've got problems with prioritization. Queues don't do prioritization. You just take it off the front and that's it. So we get around this by building more queues. We've got priority queues. We can have multiple queues, each with its own priority. To decrease contention, we can have multiple queues where different threads will always insert into one subqueue and pop out of the other side so that there's less contention on each subqueue. These are all, they work, but they're band-aids. Instead of having one problem, we now have many. We have the same problem with priority queues that we have with queues. And so you get around the priority, but now you've got things like task starvation. You've got load balancing if you've got tasks that are in queues that aren't being serviced. So we create other things like task scaling. So we've got another band-aid to get past the deficiency, all because we're using queues. I can't read that from here. This is a sweet spot where I can't read it. So I think we've gone through this. The final thing that I find problematic with queues, and it's part of a queue again, is that we tightly couple the logic, the function, the task itself, with the data to be acted upon. We do that because obviously, in order to get the data and the task, the logic at the front of the queue at the right time together, we have to package them up. Because we don't know when the task will reach the front of the queue, and it's too late to say, this is the logic I want you to apply to this data. We have to do that for tasks. We don't necessarily have to do it for queues, but we don't necessarily have to do it if we don't use a queue. So what's the alternative to the queue? if I'm going to bash queues all day long and be a queue hater, I better come up with a solution, yeah? Well, first I'll tell you about myself, and then we'll get to it. My name is Michael Maniscalco. I'm not related to Sebastian, just in case anybody's curious. I'm a software architect and principal developer at Lime Trading. We develop software for low latency trading and market data for use in high frequency trading. Personally, I have several GitHub accounts. One is my own personal stuff that's less than professional grade. It's filled with all kinds of novel data compression algorithms and whatnot that I've built over the years. And also I have a second, which is building CPP, and that's where work contracts resides, as well as several other projects, networking that's built on work contracts, et cetera. That is dedicated to building professional grade code and studying the architecture that's used using exclusively modern C++. So, what do we use to replace a queue? What is the alternative? Work contracts. In particular, work contracts is a collection of callables. For the time being, think of a work contract as a task. It's not, it's more complicated, but it helps to absorb the idea. So we create a work contract group, which is a collection of work contracts, callables. The key element is on the left side. That is called a signal tree. So we're going to replace queues with a tree, and we're going to get outstanding performance. The queue itself, the tree itself is lock-free, and at least 50% of the time, more than that, it's weight-free. So its performance is superior. And my clicker is not working. Okay, so we've gone through the signal tree itself at a high-level view. Each leaf in the tree is a signal, and each signal is coupled with a work contract. So when a signal is set, the threads can navigate the signal tree, locate a leaf node that is set, associate it with the work contract, which is the logic, not the data, and it can execute that logic. So we have threads, unlike a queue, coming in, traversing a structure, and going to the logic, as opposed to the data coming to the threads. And in this way, we can separate the threads out to different tasks, work contracts, and eliminate a lot of the contention. Most of the secret sauce is in the signal tree itself, and I'm going to spend some time on that. This is the resources for the talk, source code. I'll put this up at the end as well so people can see that toward the end. Now, I've said that it's much better than queues. The first thing I want to do is prove that. So we'll go through a few benchmarks. This is the specifics on the machine. I didn't do too much in the benchmarks to tune the machines at all. I did disable hyperthreading, but this machine has 16 E cores, efficient cores, and they're not affected by hyperthreading anyways. I did not use any of the performance cores. I wanted the test to be as many threads as possible, and that happens to be the efficient cores. And I wanted them all to be the same performance. I didn't want tests that went up and down because some CPUs work better than others. So we stayed on the efficient cores. So this benchmark will take 3 of the established best-in-class sort of multi-producer, multi-consumer queues and work contracts. We're going to use Boost lock-free, we're going to use TVB concurrent queue, and Moody Camel concurrent queue. Now, I'll caution you ahead of time. This is, of course, slideware, so it's very unlikely that it's actually going to compile. Maybe it will, maybe it won't. Forgive me if there's a typo. But I hope that the code is sufficient that we can make our point as we see it. I'm gonna have to go up to my laptop here to be able to see. So this is describing what the benchmark is going to do. At the top of the function, the top function is the benchmark itself. So what we're going to do is we're going to create a queue of a fixed size. And we're going to populate it with a task, one type of task, but we're going to populate it with a number of those tasks, copies of it. And this test is 16K of tasks stuffed into the queue. We then create some number of worker threads depending on the configuration for the test. And those threads are going to wait for the test to start by a flag. Then they're going to iterate, they're going to keep on going in a while loop until we say stop. And their entire task is to pop a task off of the front of the queue, invoke the task, and then stick it into the back of the queue. And this way that the queue will remain full and every single thread is a producer and then a consumer, or a consumer then a producer. And we'll run the test for a certain amount of time. Then we'll stop the test and we'll calculate the results. What we're going to measure here is per thread task execution. So how many tasks did each unique thread invoke during the test? We're also going to track how many times each task was invoked. So that will give us a chance to see how fairly the tasks were treated during the test. And then we can add it all together to see the actual throughput for the container in question for the test. So we're actually going to run this through, starting with 2 threads and ending with 16. So the same test will be executed with 2 threads, 3 threads, 4 threads, et cetera, up to 16 threads. And we'll run the same test for each of the 4 solutions. In the case of work contracts, it's not a queue, so its behavior is slightly different. It's going to schedule contracts in the signal tree that we saw. It's going to locate that set signal, find the task, execute the task, and then reschedule that signal again, which is equivalent to popping off the front of the queue, executing, and pushing into the back of the queue. And that will give us a chart like this, where we'll have all 4 of the solutions and their performance from 2 to 16 threads. That's one of the slides, but it's just one at random. And then we're going to actually describe the task itself. Now, the task is basically to hash a string some number of times. And that number of times is configurable so that we can have different tasks based on the duration. And we can see here, there's the task. We're going to have 4 different types of tasks. The low contention task will hash that string 256 times as one task. That takes, on this machine, about 4 microseconds. The second one is going to be medium contention, which does it 64 times. It takes about 1 microsecond to complete the task. Then we get into high contention, where we start getting into what low latency would be concerned with. These may seem like small numbers, but the goal is to be able to take large tasks and break them into tiny tasks so that we have a better performing system. We might actually have just tiny tasks, like calling a polling on a kernel bypass card. That's incredibly fast. We can't afford to have large overhead queuing up tasks like this. So that's a very relevant test. And then for fun, there's the maximum contention, which is an empty task. So this is strictly popping and pushing onto the queue, or scheduling, locating, and invoking signals. And that will give us 4 charts, 1 for each level of contention. As the contention decreases, obviously there's going to be less push and pop on the queue, so there's less contention because the threads are doing more calculating in the hash than they are actually working with the container. And so these are the results. In the low contention benchmark, which is what you would expect in the real world, just general task queue, all 4 perform about the same. Work contracts gets a little edge, not a lot. On the left side, that is the actual total throughput, the number of tasks. On the right-hand side, it's the same thing, but it's per thread. So on the left side, we want to see the line climbing. It means we're getting more performance, more throughput as the number of threads increase. And on the right-hand side, we want to see a nice flat line. That is, as we have more threads, each thread continues to do the same amount of work. That's a better measurement of the contention, because if it's contention, the threads will drop in their individual performance. At the bottom, we have 2 metrics, and they are the task fairness and the thread fairness. So the task fairness is basically a metric that says, at 16 cores, how evenly were each task executed? Do we have a lot of one task executed and very few of the other? Not fair, or all evenly, which is fair. So we want to see a very low number here. A high number means that they perform very poorly. A low number means that they've performed very well. So when you're seeing numbers that are less than 0.01, or even at the work contract 0.06, this basically means that all the tasks have been executed pretty fairly. The second metric is the thread metric. And so this is the same thing, but for threads. Did all the threads perform about the same number of tasks? Or did some threads perform much more tasks, and others, for whatever reason, in contention, performed much less? And so from this, we can see that there's only one solution that actually didn't perform well, and that's Moody Camel. And we'll see this throughout the test. Moody Camel has a number of sub-queues, and that's how they get better speed by queuing to multiple sub-queues to diminish some of the contention on the queues. But the threads that actually pull out of the other end of the queue, they tend to pull out of one queue more than the other, and you wind up with not a very fair system for task execution. And we'll see that throughout. So basically, at low latency, at low contention, everything's fine. Everybody's working great. We move on to the medium contention, and we start to see some difference. So this is at 17 nanoseconds. So this is relevant for writing task concurrency in low latency. We can see that the boost lock free starts to decay pretty quickly. I think that's at about, 5, 6 cores. It actually starts to decrease in performance. At that point, you're wasting cores. You're actually getting less done by putting more cores in. The same is true for the other two multi-consumer queues. They perform better, but they're clearly falling off toward when the number of threads gets higher. The work contracts doesn't really get much of a dent. There's a little anomaly there, but at this speed, you get one interrupt and your measurement's off by a little bit. But basically, work contracts is continuing to scale all the way along, and we can see that on the right-hand side, that it's not a flat line, but it's not diminishing as much as the other solutions are. And again, our metrics for fairness, they're all doing very well, except again, Moody Camel, which is not very good at even task distribution. I'm sorry, that was the 1 microsecond. This is the high contention, the 17 nanoseconds. And now we see where the multi-producer, multi-consumer queues just fall apart. At this point, the amount of contention is sufficient that you don't get a return on the investment. They perform poorly. I should put that as a logarithmic chart, but the point is not the numbers, but the pattern. You can see that work contracts continues to scale no matter how many threads you throw at it. It continues to go up and up and up. All of the queues, they go up a little bit, then they flatline and start to diminish and falter completely. We can notice here, this is very important, at this speed, all but Moody Camel are doing very well on thread fairness, and all are doing very well on task fairness except for Moody Camel. So they're starting to perform more poorly, but their metrics for fairness is pretty decent. And while this is not a realistic scenario, an empty task, it does prove that even when there's no task whatsoever, the amount of friction that's put on a signal tree is virtually nothing. It continues to scale even now with 1.5 microsecond, a nanosecond task, which is basically, I think, the timing, calling an empty function. And still we see the same basic metrics for task fairness and for thread fairness. Again, Moody Camel suffers, it's not very task fair, but notice work contracts. It's scaling perfectly, and it's still doing extremely well on task fairness and thread fairness. So there's no trade-offs here. It's just simply outperforming and outscaling the queues. So where is this improvement coming from? It is almost all entirely in the signal tree itself, the container that replaces queues. It is a log-free container. In a lot of occasions, it's weight-free. It allows multi-threaded access, so you can have all the threads going through the signal tree in different branches at the exact same time. There's going to be minimal contention between them because they're finding different paths through the tree, so they're not operating on the same atomics at the same time. It has excellent scalability. In the maximum benchmark at high scale, it is 40 times faster in throughput than Moody Camel, which is the fastest of the concurrent queues. It's 100 times faster than the average multi-producer, multi-consumer queue at 16 cores on the low contention. It has excellent memory profile. It's 1/2 N because it's, as we'll see, it's not really a binary tree, it's more compacted down. So having a signal tree that has millions of signals in it is not going to take a lot of memory, couple 100 megabytes at best to build large trees. So there's no memory overhead to the solution. It has excellent task selection bias as we saw in the tests. Its per thread execution is also very good. It has other benefits by going through a tree. One is that unlike a queue where you can only access the element at the front of the queue, with a tree, you can access every element in the tree. All of the leaf nodes represent a task. So you can hit them all at the same time. We'll see that there's a method for adding bias to the traversal of the tree. And this is where the fairness comes from. There's a policy for traversing the tree where as the threads navigate the tree, they'll want to navigate different ways every time that they navigate to look for a signal and therefore a contract. This can also be used on a per thread basis. Unlike a queue, we have queues, then we have priority queues. This signal tree, some threads can traverse it with priority, while others will traverse it for fairness. And we can do that, I'll show how that happens later on. So this is a signal tree, and this is the basic algorithm that's going to happen here. So the properties of a signal tree are that it is a perfect binary tree. Now, for people who've been out of CS 101 for 20 years, 30 years like myself, I had to go and look up the term. Basically, every internal node will have 2 children. Every leaf node will have no children. That is a perfect binary tree. The leaf nodes represent the signals. So if the leaf node is a 1, then that signal is on. If the leaf node is 0, the signal is off, reset. It is also a tree with child sum property. Child sum property says that for every internal node, its count is equal to the sum of its 2 children. Now, because I have set several of the signals to 1, this is not child sum property. This, however, would be child sum property. This is what we need to establish in order for this to be a proper signal tree and to navigate it properly. So, how do we set a signal? We have to begin at the leaf. The order is important. So setting a signal begins at the leaf node that represents that particular signal. Say we want to set the third signal, signal number 2. We set it to 1. And now the child sum property is ruined. So we navigate from the leaf up the tree, and we increment every node by 1. These are atomic counters. And we have our memory ordering so that it can't be reordered. The order is important. We start at the bottom, we traverse up the tree. If we wanted to set a second signal, we would set it to 1. We'd throw off the child sum property. We would traverse the tree. This one now gets set to 2, and the root gets set to 2. And we have a valid signal tree again. One observation to note is that the root is the same count as the number of leaves. So if you want to see if a signal tree has no signal set, you look at the root. If it's 0, there are no signals set. I don't think we need to go through the summary, and I know I'm going to be tight on time. So selecting signals is exactly the opposite. We have to start at the root. I'll do that again. It's 2. If we can decrement it from a non-zero value to 1 less than that, then we immediately know that that thread can claim one of the signals at the leaf. I'll leave the proof to the reader. So we decrement the root, and then we look for the child nodes, and any child node that has a non-zero value is a potential candidate for traversing the tree. In this case, only the left child is traversable, so we'll go there, and we'll decrement that, and we'll look for the children again. Now in this case, there are 2 children to select from. So at this point, we're going to arbitrarily choose the left child, but this is where the bias algorithm comes in. And I'll show how that works after we're done with setting the signals. And that can be used to influence which way the thread will traverse the tree and ultimately which signal it will claim. So we're just going to go ahead and claim the left signal. Then we're going to select the only child, set that to 0 by decrementing it, and we have selected a signal out of the signal tree, leaving us with a valid signal tree. It has child sum property restored by decrementing as it goes. Again, the order is important. It must start at the top and go to the bottom. When it hits the leaf, it knows which signal it has reset. That signal is associated inside of the work contract group with one specific work contract. So it knows that that contract has been selected for execution. Again, at this point, it's helpful to think of a work contract as a task. Again, it's not, it's more complicated, it has a few more benefits, we'll go into that. But this is how it would locate some task, some logic that needs to be executed by the thread that happened to select that on the tree. I'm going to breeze through the summaries. If people don't understand it, then I'll go back to the summary, but I know that I'm going to be short on time on this. So, how do we create the fairness that we saw in the tests? How do we get task selection fairness out of this tree? We use bias flags. Now, bias flag is basically just a bit set. We're going to use an integer. And each bit in the integer represents or corresponds to one of the levels of the tree. When the thread that's navigating the tree hits that level, it's going to prefer the left child or the right child based off of that bit. So if the bit is 0 and it has an option that both children have a non-zero value, it will prefer the left side. If the bit is 1, it will prefer the right side. But that only happens if both children have values. If one child is 0, obviously the choice is made first and we have to select the other path. So, selecting a node begins at the top. We decrement it from a non-zero value down by 1. The bias bit says it's 0, we would prefer to go to the left, which is the case because we can't go to the right anyways. So we navigate to that node. We then decrement it by 1. We look at the next bias bit, which is 0, and that says, I would prefer you to go to the left. We could go either way on this, but the bias flag comes into play here and says, I'm 0, you're going to the left. We then decrement that by 1. The third bias flag says, I want to go to the left again because it's a 0, but that child has no value in it, so it has to go to the right. It decrements that node, and it discovers that it has selected signal 1. We can also create, this is another example I'm going to walk through very quickly. So this is the same thing, but we've altered the bias flags, for example. It will navigate to the right. 0 says that it wants to go to the right. Oh, I'm sorry, I got the wrong bit. The second bit is 1. It says it wants to go to the right. So it will choose to the right. It will decrement it. Then it says that the bit is 0. It wants to go to the left, which happens to be good because the left child is the only choice. And now signal 2 has been selected. So the bias flags is basically just a counter. And every time the thread traverses the tree, it's going to increase the counter by 1. And this basically influences the path, so it will prefer to go to the first node, the first leaf, the second leaf, the third leaf, etc., just by incrementing the counter. There are details beyond that that are too complex to go through here, but with a little bit of nuance, and I can talk anybody through that afterwards if they're interested, you can get perfect selection. It would select each set node one at a time, and it would never double up. It can also be used for prioritization. So it's the same exact mechanism, only we're going to lock the lower bits. If we wanted to create a priority zone where we would want our priority work contracts, we would put priority signals in that yellow zone. And we would lock the first 2 bits to 0 and 1, which automatically forces, all things being possible, if there's a path to that yellow priority section, those 2 bits will influence the thread down to that lowest red circled node because the pattern is 0 and 1. So automatically, this thread, if there's a path to that priority section, it will go down that far. And so it would go down to the 1, and at that point, the non-locked bits would take place, and they are the same fairness bits. So it allows us to fairly choose between one of the tasks that would be set by a signal in the priority area. And you can carve up the tree into many priority areas and have different locked bit patterns to navigate and select something that's in the priority area. If there was nothing in the priority area, it's very opportunistic. It would just simply travel to some other node, to some other signal that isn't in the priority area. It costs no overhead. And it's per thread, so you can have one thread that says, it's time for me to start looking for priority tasks, and all the other threads saying, I'll take any task I can get. This is very much unlike a queue. Again, the queue, you have to take the front, or you have to build a whole new class, a priority queue. Here, you get the best of all of the worlds in one container. And we saw that the performance is outstanding. Or at least I claim it is. Never take benchmarks for my word. So that's how we create bias and how we create fairness in the tree. Again, I'm going to give a moment for the summaries, but I'm going to skip through them because I know I was timing myself at 1 hour and 2 minutes, and that's not good. Okay, so On to work contracts. So the signal tree is the secret sauce that allows us to reduce the overhead in the queue. With that, we're going to add work contracts, which is, again, think of it as a task for now, which is one task per signal at the bottom of the tree. So you select the signal, you execute that task. If you want that task executed, you set the signal, which again is lock-free, and it's actually wait-free for setting the signal. So the basic overview will be a hello world. No contract is created on their own. They're created inside of a work contract group. That's a work contract group. It comes with a signal tree, and it comes with the same number of work contracts as the leafs. So there's one signal leaf node corresponding to each work contract. In this case, we asked for 4, so we got 4. In reality, I think the minimum is 64. Then we can ask the work contract to create a contract for us. So it's going to go and select one of the available contracts, and it's going to take the callable that we have provided as the work that we want executed every time we set the signal associated with that contract. And so it's claimed one of the signals, and it's put the callable in there. Now we're going to schedule that contract. As it is right now, it's not scheduled. No thread will find the signal because it's not populated in the tree yet. So we're going to set the signal in the signal tree just as we had in the examples. You start at the root, associated with the signal to the work contract that you're trying to select. It goes up the tree. Order is important, leaf to root, and it increments each node by 1. Next, we're going to go back to the work contract group, and we're going to say to execute the next contract. Now, in this example, there's one contract, so we know which one is going to execute. In the real world, there may be millions of contracts. Half of them might be set, so the signal tree will be very populated with possible paths. So calling execute next contract is that thread finding some signal somewhere based off of whatever traversal policy we have, fairness or priority, and it will try to travel down the tree. This is the inside of the execute next contract, a simplified version. It will select an element from the tree, just like always. It will go from the root, and it will decrement down. When it finds a signal, it knows exactly which contract has been set, and then it will go into its contracts and invoke the contract, which will give us hello world. So this is a hello world minimal example of using work contracts. Simple and boring, but comprehensive. I'll skip through the summaries. So, as I said, work contracts are not really tasks. It's helpful to think of them that way in the beginning, but they have internal state. They also support, and I'm going to shadow a term here that I shouldn't shadow, a destructor. It's not really a destructor, but it's analogous. So work contracts not only can execute asynchronously their contracted invocable function, they optionally can invoke asynchronously a callable at the time that they're destroyed, which comes in handy because work contracts are expected to be long-lived objects. They are only logic, they're not data. So work contracts that say calls receive on a socket, it's not a one-off. You want that contract to stay around because you're going to call receive on that socket many times. Every time a poller pulls that socket, it's going to turn on its signal saying, somebody come and call receive on me. So it's a long-term object. That's one of the reasons that destructors here are very good. You really don't know exactly when this contract will expire. So again, we create a work contract group. Again, we ask that contract group to give us a contract, but this time we provide a second argument. This is the release function, as it's called in the code. Basically, it's a destructor. We schedule the work contract because, again, it's not scheduled when you create it. We call on the work contract group to execute a contract, and we'll do exactly what it did in the previous example, which is to navigate down the tree, locate the contract, and execute it. So it's now executing the contracted function that it can do again and again and again. Next, we will say onto the contract release. This is basically saying, I don't want you anymore, but it doesn't get destroyed immediately. It gets destroyed asynchronously. So calling release will go back to the signal tree and turn the signal on again. But internal to the work contract, it marks itself as expired. So as it gets serviced on the next call to execute a work contract, again, it will go down the signal tree. It will locate that work contract, but now it will see that the state is set to be destroyed. So instead of invoking the primary function that it's contracted to do many, many times, it will call by just once the destructor. And this is the destruction routine, one of the multiple handlers inside of a work contract. Work contracts also have, I didn't put it on the slides, but it also has a third callable, which is to handle exceptions. So if your primary function throws an exception and you don't catch it, or if your release destructor throws an exception, then they can get routed to a third callback, which is to tell you which contract and what exception just happened. I didn't put that in the slides because I didn't think we were going to have time for it. So basically, this is how work contracts work. They're a collection of callables under one container with state. There are several advantages to the state. We'll go into that in a moment. So work contracts, as I said, are long-lived objects. They're not intended to be invoked once like a task. They're intended to be invoked many, many times. And that is why we separate the logic from the data. Data you want to use once, but the logic you want to do many times, right? We don't call a function once, we call it again and again. So it has repeatable invocations. And this is a quick example of that. So here we, again, create a work contract group. We ask for a work contract, but our contract is going to be this lambda that has an I in it, and it's mutable, and it's going to print out what the value of I is and then increase I. So we schedule a work contract, which will set the signal in the signal tree. Then we call execute next contract. It will navigate from the root to the leaf, find the signal, find the contract, and execute the primary function. And there's a typo because I have mutable in there twice. And it will print I. Then we will schedule a contract again. So it will go back to the signal tree, and it will populate from the leaf to the root, setting the signal up again. We call execute next contract again. It will go back and execute the exact same callable. This time I is 2. And it's executed again. So we could put this in a loop and keep on repeating it. Work contract's primary function is repeatable and it's intended to be long-lived. Now, as I said, it has only logic in it. It doesn't have data. So the way we would get data into a work contract is user-defined. Some contracts don't have to have input. A contract that calls socket receive does not need to know any input. It just needs to know what the socket is. And we would capture that in the lambda's capture. Some need input. So when you need input, you would usually capture some kind of reference or pointer to a queue. Now, I just spent half an hour bashing queues. Queues are good. They're fantastic for data. They're not fantastic for logic. So we have a queue that we can connect and capture into that lambda. And every time it's invoked, we would go to the queue and pop something out and use it, and we would operate on it with a logic that belongs inside of the work contract. Now, one of the things to keep in mind, and I haven't made it obvious yet, is from the internal state of the work contract, only one thread that navigates the signal tree will be able to claim the set signal. No other thread will be able to do it because the tree is adjusted atomically, and only one thread is going to be able to turn that leaf node from 1 to 0. Therefore, only one thread will execute the primary work contract function at a time. So it is, in essence, thread safe. It's single-threaded. Everything that's inside that contract, I'll go back one step. That print line can only be executed by one thread at a time, whichever thread happened to claim the signal. So if we were going to have an ingress, some kind of queue coming in, it would be a single consumer queue because there's only one thread active at a time. We don't need multi-producer, multi-consumer here. We just can use a single producer, single consumer queue, which is significantly more scalable than a multi-producer, multi-consumer queue. So we have no locks. We have a really efficient way of putting data directly into the work contract. The work contract is just the logic. And unlike a task queue, where tasks can have different data and different logic, this is data specific for this logic. So this queue doesn't have abstractions, no base class like a base task class would have because we don't know what the logic is going to be. This is just data that's consumed by that logic. So it would be a single producer, single consumer queue of packets or integers, but they're all the same type, which is very efficient. And that's the summary. Now, The callable, the contract primary work function can also accept a work contract token. Work contracts are move only. So you own the work contract on the outside, you can't get a reference to it on the inside. So we have a token. And so this is the exact same or very similar example, but the callable, the work contract accepts a work token function, token. And that token is basically handled back to the work contract that's being executed. And so here, we see that the token can call schedule from within the execution. So if the logic inside of the work contract says I need to happen again, you can use the token while it's being executed to reschedule itself immediately. You don't have to do it from the outside. And similarly, the token allows you to release as well. So if you've got logic inside of your primary work function contract that says it's time to go and release, you can do it this way. So we have a very similar example to the previous one. We have a destructor destroyed just so we know the test is over. And we're going to go through with it until done is set. And you can see here, done is set when the destructor goes off, the release function. So all we're going to do is in a loop call execute next contract, which will take the scheduled work contract, travel the signal tree from the root to the leaf, locate the contract, and execute it. And it will increment I, it will print 0. I is now 1, it's less than 2, so we schedule again. We don't have to do it from outside. Then it will, the main thread will execute again. This time it will go through, execute the primary function, print I is 1, increment it, but now I is not less than 2. So it will go to the token release, which will, again, schedule the contract, but also flag it internally with its internal bits to say that it is now time to destroy this object. But we're not done yet. So again, the outer loop will execute the next contract, but now because it's set for destruction, it will traverse the signal tree from the root to the leaf, the work contract, and it will invoke the destructor, which will print destroyed, set done, and the main loop can then exit. So this is how we can use the internal states and how we can add the logic inside of the primary function as to whether we want to schedule again or destroy or do nothing. So obviously this is pretty boring at this point because we have just the main thread calling execute next function, execute next contract. So here we can create a work contract group. We can create a group of threads captured by reference to the work contract group because this is slideware. We can say while the stop token is not requested for the stop, go ahead and execute next work contract inside of the work contract group. And we can create a whole bunch of threads and they can all service the work contract group at the same time. They're all going down the same signal tree, but they're finding different paths. Some of them might be priority, some of them might be fairness, and they will navigate in different paths if they can decrement the root. If there's only one signal set, the root will be 1, and all the threads will fight for that one decrement to 0, find that one contract and execute it. But if many contracts are scheduled, they'll find different paths. They won't compete, unlike a queue, which keeps hammering away at the head. They'll travel different parts of the tree. They won't contend with each other at all, and the performance will be fantastic. Oh, I shouldn't have faded between. So, and then we're going to take the thread that did the execution, we're going to dump its ID to the console, and we're going to increment I and print that as well. And then with the token, we're again going to reschedule that contract. Whoever executed the contract will reschedule it again, so it will keep looping. We'll kick it off by scheduling the contract in the first place, and then we'll sleep for 10 seconds. And this contract will keep re-invoking again and again and again, but different threads, hopefully, will service this particular contract. And we can see that it does. At least I drew an example where it did. So these are different threads, all the different threads competing to enter the contract again and again and again, rescheduling as they dump to the console, printing I in order. Now notice that the output is not mangled. All the numbers are in order. We don't get print that's overlapping each other, and that's because the work contract is guaranteed to be executed by one thread at a time. So we have this thread safety built in. You don't need synchronization, and it just works. This one is basically the same thing, but we're going to go a little bit further. We're going to create a single producer, single consumer queue. We're going to create a work contract group. We're going to create our worker threads just like before. They're all going to go in a loop until they're told to stop, and they're going to execute the next work contract. We then create a work contract, same as before. It will dump the ID. It will pop from the queue. Now, by reference, we have captured a reference to the queue. And because it's single producer, single consumer, but because work contracts are executed by one thread at a time, it's totally safe. Pop off of the queue. If the queue is not empty, and only if it's not empty, we'll reschedule the work contract, because we know the queue's not empty, there's more work to do, reschedule it, reset the signal, some other thread will come in. If it is empty, we want to leave the signal in an unset state because there's no reason to drain a queue that's empty. The main thread will count from 0 to 8K, and we'll push that integer into the single producer, single consumer queue, and when it's successful doing so, it will schedule the contract. Now, it's not obvious here, but when you schedule a contract and then you schedule it again, if it's already set, that won't mutate its state anymore. So it's either set or not. So if both the worker thread said token schedule and the primary thread, the main thread, said work contract schedule, it doesn't matter. It will just be scheduled. It's not scheduled twice. You can't schedule twice and then expect 2 executions. It's just set. It's a signal. And so with this logic, it's always safe to pop from the queue because the signal is only set when we know that there's an element in the queue. And the main thread, will just keep on looping until the queue is empty, which means that the worker threads have processed the contract enough times to drain the queue out. And we get the results that are very similar to the previous. We get different threads consuming from the single producer, single consumer queue, all in order, no mangling because it's guaranteed to be executed by one thread at a time. So, in summary, we have a container that outperforms by large amounts queues. It does that because we question why are we using a queue in the first place. It's a good container. It's great. We like to queue things, but we don't queue logic. It doesn't make no sense. Would you imagine writing your code line by line and queuing those instructions in a queue and popping them off and executing? We don't need that. We write our code, our logic, in a logical fashion. And so too, you could take your code, which would be call function 1, call function 2, call function 3. Just break it into contracts. Put function 1 in a contract, put function 2 in a contract, put function 3 in a contract. When function 1 is done, it takes the output, puts it into a single producer, single consumer queue, and it sets the signal on the second contract, which then goes off, takes the data out, executes function 2, puts the data into a single consumer queue, sets the signal for the third, and we basically have broken code that would be call function 1, 2, and 3 into concurrent code. And it's asynchronous executed by the worker threads. So we have something we've seen by the benchmarks scales incredibly well. It minimizes contention. It offers prioritization. It prevents any possibility of task starvation. We don't have to have work stealing because every single task is available at all times in the signal tree if they're set. And we built a system on top of that with work contracts, which have built-in destructors, internal states so that they know when they're to be terminated. They have a repeatable invocation so they can stick around for a long period of time. The logic is encapsulated inside of the work contract, which I find personally much easier to read. I deliberately stayed away from adding concepts like continuations and things like that to work contracts. Basically, I think it's one of the important things here to note is that it's not bringing new concepts that the developer would need to know to use work contracts. If you understand what a lambda is, you can use a work contract. You don't need to know anything about under the hood. You can create a contract, stick your lambda in there, schedule it, and execute it. There's no possibility of deadlocks. You've got super high performance. There's no possibility, unlike say in coroutines, of dangling references and lifetime management of references. None of that is here. If you understand lambdas, you can use work contracts and you can get superior performance to the standard task queue. So those are the points that have been presented here. Hopefully that is somewhat convincing that we don't need to use queues for everything. Queues are great for data, not so great for tasks, for logic. And with that, I thank you for listening. And if you'll indulge me for a moment, I'd like to thank my wife who puts up with me while I work on all of this stuff, and my daughters who drew a lot of the little characters throughout the thing. Lime Trading, thank them for sponsoring me to come out here. And to my colleague Andre, who's a very disciplined man, and in his Russian accent, he took a look at my slides to review and help me. And he said, Michael, I'm for you, but these slides suck. So I went back and I spent a lot of time redesigning these with his counsel, and I hope it worked out well. And I hope you enjoyed the presentation. With that, if anybody has any questions, there are microphones on both sides. There's the references again. Now, I apologize, it's a complex thing. There's a lot of new concepts in the trees and all of that, but I wanted to give a brief overview. Hopefully it's enough that people understand, but if anybody has questions at all, hopefully not too complicated because it's difficult to explain a lot of the nuances, but I'll do my best. Yes? I can't. Is that microphone on? I can't hear.
Test. Oh, this one's on.
Test.
Okay, I can hear.
So thank you for the talk. I'm just sort of wondering, how would you go about implementing parallel algorithms as part of this sort of work contract? Is that something that you support, or can it be built on top? Or?
Oh, as I said, I try to keep this minimalistic and not have continuations or any of that. I think these are things that are being well solved now or will be in the near future by other techniques. I'm hopeful that if anything, say under senders receivers, any implementation that has something like a task, you might say, hey, wait a second, maybe we can do a little better with the signal tree. But I did not go any further down that path. I wanted to keep it simple as basically a tool, but not a comprehensive solution. I do have plans in the future to add that as needed, but I'm sort of taking a step back and let's see what happens with other solutions that may be able to do it really well now. So.
Okay, thank you.
Hey, Michael.
Hey.
So,
I'll make it too hard a question.
Well, I hope this one's not too hard. Very awesome talk. I really appreciated it, and I actually am well convinced. There's one area that I'm a little not sure about, and it's about the concurrency or the thread safety of the signal list. So what was going through my head was, we're going to dispatch from the top and start decrementing atomically, and then we're also going to add items from the bottom. We're going to start adding atomically.
Yes.
And this thought that came to my head was, what happens if they kind of meet in between? Is there a chance that something? Yeah.
No, actually, that's a good question, and I've thought about this a lot. So if you have an existing path from the leaf, say it's going this way, and then it goes up to the root, and you have a new signal, which is as you're traversing down and consuming this path, and another thread is setting a signal, as they cross, the consuming thread could go either way. All it knows is that there's a left and a right child. And it will consume one, and the producing thread will undo the consumption that the consumer did. It will recomplete the path of the existing branch. So as they cross paths, the consumer will just choose a path, and the producer will restore the path that the consumer has already taken away. So it's perfectly safe for them to cross paths.
Awesome, thank you.
Yep.
One thing that wasn't clear to me was how you prevent two threads from executing the work contract at the same time.
Okay, there's two parts to that. One is the signal tree itself. Because as you traverse the tree, you pick a child, and if you can decrement it down by one, then you can navigate that path. If another thread happens to be also competing, which is rare, then you would have to go again, which is why it's lock-free but not wait-free. You'd have to wait and try again, maybe on the other path. So think about it as you get closer to the leaf node, you're the parent of the leaf node. It can only be 0 or 1.
Yeah, but what if like another thread schedules the work contract while someone else is executing it?
Oh, there are internal state bits that prevent that. So what happens is, I don't want to get too deep into it, but the first two bits in the state flags inside of the contract, the first one says that it's scheduled. The second one says that it's being executed. So any thread that schedules a work contract sets the first bit. It does that with just a fetch or, I think it is that I used. And if the result comes back that the second bit is set, somebody's already executing it, it won't set the signal in the signal tree. Instead, it'll walk away. And when the thread that is executing, that owns that second bit, is done, it's going to clear that bit away with a fetch and to wipe out that bit. And if what it sees is that it was already scheduled while it was working, it will complete the signal tree.
Okay.
So it can't be set while being executed. But
the thread can reschedule. Well, the work contract can reschedule itself, so that just has to get handled specially. Like your examples where if there's something...
It falls into the same logic. It will go and set the first bit saying, I want to schedule, but it will notice that the second bit is already set because it's executed.
Oh, good. Yeah, I see.
And so it will give up. And as the contract exits, the logic will wipe out that second bit and look at what the first bit was and then resume the scheduling.
Okay, thank you. I appreciate it.
Question?
Yeah, so I had a question about, like earlier you mentioned the reason why the queue system is slow is because all the threads are looking to the same location. So there's like high contention. So, but like in the signal tree system, all the threads have to look into the same root node.
Root node, yes.
Yes. How do you do that?
I gave a very simple diagram of what the signal tree is because it's easy to wrap our heads around a binary tree. In fact, stars, it's not really a binary tree. It is, but it's more like a trie. So everything is compressed down and counters are added together in the same 64-bit ints. And we don't have deep trees. Under the hood, it's actually multiple signal trees. And so different threads will choose different trees at different times. And to find a tree, when you actually say create a work contract, there's an algorithm to go and find the maximum distance between existing contracts, and it will fill the gaps in. And what that has an effect of doing, unless you create a tree with 10 billion contracts and you set 2, if you have a fair size, which is usually about 4 times the number of contracts that you expect to use, and it's so memory efficient, that's not a large overhead, you can have many, many trees. And you're not going to spend all your time scrolling through the top of trees to find one that has a non-zero node because you've distributed your contracts between the trees. So almost any tree that you hit will have a contract, but almost no 2 threads will be competing on the same root at the same time.
I see. That makes a lot of sense. Thank you so much.
That actually kind of leads to my question, and you kind of answered it. My question was, what happens if you try and schedule more work contracts than you have leaves? And the answer is, it doesn't work.
It won't find a contract. It will return a null work contract. The contract knows it for itself that it's invalid. I didn't put that in the slide. I didn't do a comprehensive job there. I apologize.
Thank you for the topic. Appreciate it. So my question is, like, sounds like all the tasks or the contract has assumption that there's no memory locality issues associated with it. Like, if you're running something on a different thread, you may have a lot cache issues associated with it. So how you design this to deal with that?
Well, this isn't something that I've implemented yet, but we can actually set by bias bits. We can take each thread and give them a certain bias all the time. It's not for priority to a particular subset of the tree, but it is. So it would be, okay, this thread would prefer to service this half of the tree or this 5, 6 contracts over here. It's not so much priority. If there isn't anything set there, it will go find some other work to do. But in general, it will find the same contracts again and again when they're active. And presumably that you won't have caching issues because it'll be hitting the same ingress containers or queues or whatever you have. So it should prefer to hit the same, have good cache locality because it always prefers to go to the same contracts with the same data inside of it. But I haven't implemented that yet.
Okay. Does that imply that when you add a signal into a tree, you also have that logic embedded there, saying, oh, I have somehow understand that, I have to do this?
Yes, I have to. I try to be very reserved about adding new features until I understand the ramifications of it. And while I have the solution there, I'm not sure about the best way ergonomic way to say, I want a contract, and by the way, I want it to be in this range.
Yeah.
So I have to think about that. It's going to be some kind of filter, some kind of range. So when you create a work contract, you say, I want it to be in this range, and it will prefer to give it there. And if it can't because all those signals are taken, it'll come back and say, try again. But yes, I thought about that as well, because one thing that can kill low latency is cache obliviousness.
Yeah.
And so adding this should prevent that. If we have something that's really cache sensitive, we create a small span of the tree and say, those work contracts are specifically for this thread. And if they're not set, that work contract can go off to a different direction and do some other work because there is no high priority, or of course that could obliterate the cache for that particular CPU as well. So there are implementation details. I've considered it. I kind of got a solution, but I haven't implemented it.
Got it. Thank you very much.
Mm-hmm.
Hey, Michael, great talk. I was wondering if you could help us identify, or whether you have identified any trade-offs compared to traditional task queues. For example, it seemed like the number of work contracts is limited. That seems like a...
It's not. You can create, everything under the hood is actually powers of 2, and it's got tons of context experts and so forth. So what it does is it creates a sort of a maximum optimal signal tree. And if you ask for more, it'll just create more of them. So you can't run out.
Any other trade-offs? That's what I'm curious.
There's one trade-off, and I have a solution for it, but I haven't quite figured out how I want to implement it. With queues, a thread pops off the task, and then it walks away, and it can execute that task. So it's not blocking anything while it's doing the work. So in a work contract, as is now, since it's single-threaded, you might have a single producer, single consumer queue coming in, and you'd like more than one thread to execute that contract at the same time and pop more data off so they can act on the same data in concurrent, in parallel. So that doesn't exist yet. I do have a solution for that, but again, I'm pretty reserved about implementing things until I really get a good solution. But the solution that I have in mind is that it is still single-threaded. One thread will come into the work contract, but it can forfeit through the token its single-threaded nature. So it can do all of its single-threaded things, like take out of a single producer, single consumer queue, and then call through the token and say, okay, let another thread in. Go ahead and schedule it again. I'm not exiting yet, but another thread can now come in and it can enjoy that same single-threaded up to the point where the token says, let another thread in. And that would solve that problem. The only problem with that is that you then have to keep a ref count on the number of threads that are inside the work contract and avoid and prevent the destructor from going off at the same time. And I have a solution for that, but I haven't implemented it yet, which is that when you jump from scheduled to executing, I don't actually flip the bits, I just add one. So it's an atomic add, and 1 becomes 2, clearing out the 1 bit. We can take the bits that are further out in the range and add to that. So we could add 8K and 1, and the upper bits automatically with that operation become a ref count. So I just haven't figured out exactly the logic to prevent the release from happening while threads are in, but there's a solution that's 99% set in my mind. Hasn't existed yet though. But that's its one limitation, and you can get around that. You could get a shared reference to the queue and stuff it in multiple work contracts, which could go off at the same time. They each execute their own copy of the contract, but you'd have to have some synchronization because they'd be referencing the same queue. Like at that point, you might. You'd have to set that up front. You would set that up front. The work contract group takes an argument which says how many contracts you want. So you could allocate millions of them if you wanted, because the memory footprint is 1/2 N. It's very tiny because everything is compacted down. For instance, the counters for the leaf nodes is just 1 bit. So a 64-bit atomic represents 64 leaf node counters. And you have to come up to the mic. I can't quite hear what you're saying. And also, nothing prevents us from creating second work contract groups.
Yes. Oh, I'm sorry. Maybe I got something wrong. But well, if you want to run the same contract, like not physically the same, but like semantically the same contract on multiple threads, then there is a question: how many contracts I need to have? And it seems like it should be at least as the number of worker threads, no less than. Otherwise,
probably yes. You'd only be able to scale up to the number of threads that you have.
So you need to know in advance like what the number of workers are.
Yes. It's a it's a patch for a limitation that two threads can't execute at the same time. But as I said, we do have this solution for ref counts. I just haven't implemented it yet, at which point you could have multiple threads entering the same instance of a work contract.
Thank you.
Question?
Yeah, I have a question on how do you implement the atomic decrement in the selection tree? Because I assume you have to keep comparing that value to 0, right? Like how do you...
You mean on the select where we start at the root and head down? That is the only non-weight free part of the code, and so that's basically a compare exchange.
Oh, okay.
We look at if we see that it's 0, we don't try. If it's not, we try to decrement from what it is to -1 less. And if we can do that, then we know that there's a path we can consume. We don't have to worry about running out of a path, because the root node always contains the number of signals set at the bottom. So if we can atomically decrement by compare exchange from an n to n-1, then we know there's a path we can consume going down. It's still compare exchanges all the way down. But in practice, these trees are actually pretty shallow. Okay. As I said, it's not a binary tree. What it is we have 64 leaf node counters. We only go up to 1 in a 64-bit atomic. And the parent node is actually a 64-bit counter with 8 counters embedded in it. Each one represents 64 children. And so it's not like we drew here for simplicity. Just having one parent node, we can cover 512 contracts. So there's only one atomic compare exchange. And when you get to the leaf node, you don't need to use a compare exchange. You can just use a bit mask. It's a fetch and see what comes back and see if you just cleared that particular bit, which means you've decremented that counter from 1 to 0. So the trees in practice are very short. They can be 2 or 3 levels high, but it's not that many compare exchanges. And compare exchange is not that slow if it's not in contention with any of the threads. And as the system is designed with multiple sub-signal trees, it's unlikely that the threads are competing on the same nodes. So it's reasonably efficient. And this is that benchmark I showed had 16 threads racing around, and they didn't demonstrate any degradation from that kind of competition.
Okay, thanks.
You're welcome. No other questions? All right, I guess that concludes the talk. Thank you again for listening.